Hello, everyone. Welcome to today's webinar. I'm Melissa O'Mara, Forensic Science Consultant and CNEN Media Group. I will be moderating today's event. This webinar is titled Hydrogen Utilization in Chemistry, Safety, Technology, and Applications in the Lab. It is being sponsored by Hydrogenation North America. CNEN works with sponsors to identify topics of interest and value to CNEN's audience and consistent with CNEN's mission to provide news and analysis of the chemistry enterprise in a timely, accurate, and balanced fashion. Please note that CNEN does not endorse any company, products, or services that may be mentioned in the webinars. Each webinar will be archived at CNN online after the live webcast. The presentation today is being sponsored by Hydrogenation North America. Hydrogen's product lineup includes a full range of chemistry and biology tools designed to increase lab productivity, including the H-Genie. Hydrogen's goal is to give their customers the ability to focus on their research. Accomplishing this is done largely in part by providing best-in-class service and support for solution-oriented equipment. During the presentation, we will be hearing from Richard Jones, Dr. Neil Langerman, Dr. Gallet Schipos, and Renee Labelle. Richard Jones is the CEO and founder of Thales Nano Energy. He joined Thales Nano in 2004, where he started as chief research chemist, helping to develop the H-Cube and other flow reactors, including the H-Genie. Richard studied chemistry at the University of Bristol, where he graduated with honors. He has published over 20 scientific papers, books, and patents specializing in flow chemistry. Dr. Neil Langerman is the owner and principal scientist at Advanced Chemical Safety. He specializes in issues such as chemical production, regulatory management, spill response, toxicology, and labeling. Dr. Langerman has a PhD in biochemical thermodynamics from Northwestern University and a BS in chemistry from Franklin and Marshall College in Lancaster, Pennsylvania. He currently consults on chemical, safety, and regulatory issues and has received the Tilsman-Skolnick Award for contributions to the field of chemical health and safety. Dr. Gallet Schipos received his master's degree in chemistry from the ELTE University in 2011 in Hungary. He works at Thales Nano in Hungary as a research chemist between 2011 and 2012. Dr. Schipos obtained his PhD in chemistry from the University of Western Australia in 2017, focusing his studies on asymmetric lake transition metal catalysts. In 2016, he joined the MTA ELTE Catalyst and Organic Synthesis Research Group in Budapest, where he worked on the development of visible light-driven photoredox catalysts. He currently serves ComInX as an associate principal scientist and team leader, where his main responsibility is the development and implementation of new methodologies. Since 2019, in February, he also serves Thales Nano as project manager of the Lab of the Future project. Dr. Schipos' research interest includes organic and organometallic chemistry, catalysts, photochemistry, asymmetric synthesis, ligands designs, microreactors, and continuous flow synthesis. He is also co-author of 16 peer-reviewed articles. Renee Labelle is a scientist at the Center for Continuous Flow Synthesis and Processing, part of the Research Center of Pharmaceutical Engineering in Graz, Austria. After completing his master's at Graz University of Technology in the field of synthetic organic chemistry, he joined Professor C. Oliver Cappe's research group for his PhD studies in early 2017. Since then, he has been working on industrially relevant flow chemistry projects with a focus ranging from gas-liquid reactions and liquid-liquid extractions to the implementation of process analytical technology for inline reaction monitoring. During the webinar, you can adjust the size on your screen by grabbing the lower right corner with your mouse. If you need technical assistance, please look at the Help widget at the bottom of your screen or type your query into the Q&A box. If you are disconnected during the webcast, please log in again according to the instructions you received earlier. You are encouraged to contribute to the success of this webinar by asking questions at any time during the presentation through the Q&A box on your screen. The questions will be answered at the end of the presentation, and as your moderator, I will be posing as many as time permits. So let's get started. I will now turn it over to Richard Jones.
Okay, thank you, Melissa. This is Richard Jones from Thales Nano Energy. So I will start the presentation. We have a pretty packed presentation, and you're going to learn about all things hydrogen. So at the start of the presentation, I will talk about the hydrogen and the sources of it as well, where we actually apply this in chemistry and in other areas, specifically analytics, then moving towards hydrogenation. And then, of course, what is very important, we have a section on how to handle hydrogen safely before using the example where we use a hydrogen generator with a pressure vessel. And then after that, we will move on to how a company specifically uses hydrogen to synthesize novel molecules. And then we'll, at the last presentation, we'll end with a university group and how they actually utilize flow technology to scale up hydrogenation. Okay, so when we actually look at hydrogen gas and how much we use every year, it's a vast amount. So every year, 70 million tons of hydrogen are used. So to give you an example, for every ton of hydrogen, we're talking about 11.2 million liters. This adds up to literally trillions of liters of hydrogen used every year in different applications. Now, when we look at that, there are two main applications. There's one as an energy vector, and the other is actually for feedstocks. Okay, so I won't be concentrating on the energy side in this presentation, but I think it's important to note that hydrogen is not classed as energy itself, it's an energy vector. So it is only actually utilized for the transportation of energy and actually the storage of energy, but to actually produce energy, it has to be converted into something else. So what I will be doing in this presentation is focusing on the chemical feedstock side. So where do we actually get our hydrogen to actually utilize for our chemical feedstocks? Well, there are two main methods. The first one, and this accounts for 95% of all hydrogen that is produced, is something called steam reforming. Now, what steam reforming does, it actually takes a fossil fuel source such as natural gas, which is majority of methane, and it takes that, reacts it with water to produce carbon monoxide and hydrogen, a mixture called syngas. Now, the hydrogen is then separated from this mixture, and then it can actually be supplied directly to a site or packaged into cylinders and actually sent to a site that way. Now, obviously, the one advantage of this is actually probably the cheapest way of getting hydrogen, but people are trying to investigate different methods now to get away from utilizing a fossil fuel source. But not just that, when it comes to actually the cylinder delivery, you have basically, in terms of all gas cylinders, over 60 million produced in the world every year. And with that, there are over 12.5 million truck deliveries to actually deliver those cylinders to your door. So this means that there have been a lot of research to utilize electrolysis, mainly on site, where hydrogen is generated from water electrolysis, and the electricity supplied for that is actually through renewable energy, something like solar or wind. So on the previous slide, I mentioned the process of producing hydrogen called electrolysis. And the HGenie here is an example of an electrolyzer equipment, specifically a hydrogen generator. So what happens here is water is the hydrogen source, and what we utilize is an electrolytic cell. So the water is actually applied at the anode side, and the hydroxide ions are oxidized to form oxygen. Then what you have is a process across polymer electrolytic membrane where water transfers across that along with protons to the cathode side, where the protons are actually reduced down to form hydrogen with a little bit of water, and then the water is actually dried and you have the hydrogen part there. Okay, so there are many different types of generators on the market. but they all tend to be low pressure. So the H-Genie here was specifically built and patented to actually be able to generate up to 100 bar, which is about 1400 and PSI, 1450 PSI. For this, we require a special cell architecture built out of titanium. So once you get your hydrogen, what is it being used for when you're talking about chemical feedstock? Well, the number one by far is for ammonia production. That's a whopping 55%. And then the second on the list is the petrochemical industry, obviously, because they make a fantastic amount of products actually utilizing hydrogen. That accounts for 25%. And then another 10% goes into methanol production. So those three itself actually account for 90% of the use of hydrogen every year in chemical feedstock terms. And so you're just talking about 10% when we're looking at all the hydrogen and hydrogenation that is being used in day-to-day labs. So typically in this case, what we're talking about is hydrogen being provided for GCs, or hydrogen being provided for small-scale and large-scale hydrogenation in a variety of different industries such as pharma, agrochem, flavors and fragrance, food, and also the electronics industry. So as mentioned briefly in the previous slide, hydrogen can actually be utilized as a carrier gas to supply GCs. Now, hydrogen is one of three possible options when it comes to carrier gas. So the other two gases are helium and nitrogen. So when we look at nitrogen, nitrogen has a low linear velocity, so you're not able to process so many samples. It takes a long time to process each one. So helium covers about 95% of the market, but users are now looking towards adopting hydrogen instead. And why is that? Well, the main reason actually is down to price. So helium itself is a finite resource. We tend to get helium from underground stores because actually once it gets out into the atmosphere, it literally floats away. So a lot of helium is wasted every year in birthday balloons when we should be looking to keep the reserves that we have and utilize them for medical applications such as MRI machines. Of course, you could use hydrogen for party balloons, but I guess they wouldn't be very compatible with birthday candles. But anyway, hydrogen is now looked on as a possible replacement for helium because it has a high linear velocity, so you can actually process a lot of samples. This is also very important when it comes to utilizing long columns in your GC. So the disadvantages tend to be safety, which we'll come to in a moment, but also the fact that it's not as inert and can actually react with some chemical samples. Okay. But regarding the safety side, you can use the H-Genie, which we mentioned earlier. It is capable of generating 1 liter per minute, so it's able to utilize or combine with 8 GCs and supply hydrogen to them simultaneously. However, when we're looking at chemistry, sort of the main application that we want to apply hydrogen is hydrogenation. So I'm sure that the chemists listening in are fully aware of what hydrogenation is, but for those who aren't, it typically is a chemical reaction involving the addition of hydrogen to a molecule, and you would utilize a catalyst. This is to avoid using very high temperatures and pressures. So what the catalyst does is increase the reaction rate by providing an alternative mechanistic pathway also with a lower activation energy. Now, in terms of the catalysts themselves, we tend to use either homogeneous or heterogeneous catalysts, and the heterogeneous catalysts tend to be favored just because you can actually separate them out very easily through filtration. The homogeneous catalysts tend to be used for more enantioselective chemistry. Some examples of heterogeneous catalysts are palladium, carbon, and uranium nickel. Now, I'm sure the three pictures in front of you will be very, very familiar. First one is the balloons. Now, in many cases, in many companies and universities, you're not really allowed to use balloons. There have been many people who have lost eyebrows in that particular process, but obviously they're very simple, cheap, limited to use, but you can't really do a lot of really substantial chemistry in that way. And then obviously when you move over to the sort of the pressure vessels or the par shaker, you tend to be able to at least apply a little bit of temperature, but the pressures tend to be limited unless you go for sort of the higher pressure vessels that you would get from PAR or Bookie or AMAR, for instance. But they tend to be very simple and robust and allow you to do some sort of higher chemistry. And then, of course, we have the flow reactors, which we tend to be becoming more and more popular. These also have high temperature and pressure capability. I think the main advantage is that you can actually run multiple scales. You can run sort of like a small optimization study and then actually scale up to larger quantities on the same reactor. Now, hydrogen or hydrogenation is a very useful reaction in chemistry, and it's also very popular despite the safety issues. Some sources say it accounts for between 5 to 10% of all reactions that take place. Okay, and you know, there are many different types of functional group conversions that you can do. So anything from, say, double bond reductions that you see in the Pashmanol example. That's one of the important reactions from the flavor and fragrance industry. Or next, when you look at things like debenzylations or CPZ removals, or nitrile reductions, nitro reductions, triple bond reductions, oxime reductions, imine formation and reductions. There are many, many different types of reactions, and that's what makes it so popular. Okay, and when it comes to talking about hydrogenation, pressure is particularly useful. Why is that? Well, if we look at the table on the right-hand side when we look at solubility, if you go down, hydrogen itself is not very soluble in a lot of solvents at room temperature and pressure. Okay, so that's, if we have a look at Henry's law, if we want to increase the solubility of hydrogen in a particular solvent, pressure is very important for that because it improves the solubility in that solvent, and then once the hydrogen gets into that solvent, then it can then absorb onto the catalyst surface itself. What this does, it tends to increase reaction rates by orders of magnitude, especially if we combine it with increasing the temperature of the reaction as well. So, for instance, if you're doing a reaction, so the more difficult ones under a balloon, in some cases this can take days. But then if you actually take that, increase the temperature and pressure, put it in a pressure vessel, then you can actually reduce that reaction time down to a couple of hours. However, when talking about hydrogenation in general, especially when applying temperature and pressures, it's very important to consider the safety side of things. And so what I'm going to do now is hand over to Neil, and he's going to go through all those aspects for you.
Thank you, Richard. I'm going to discuss some of the safety aspects of handling hydrogen, particularly hydrogen in cylinders. As with all chemicals, they can be handled safely, just have to follow the applicable rules and best practices. I'm going to take a ramp approach to this discussion. Associated particularly with hydrogenation, we'll look at the best practices for hydrogenation to mitigate those risks, and then some emergency response aspects, or preparing for emergency response. The takeaways from this section be that with hydrogen, what you don't recognize can hurt you. Scale really matters. The risks associated with handling hydrogen in a cylinder are significantly more than the risks of handling hydrogen from an electrochemically generated source. And regardless of how you're generating or handling your hydrogen, you need to know what to do if something goes wrong. Or recognize the hazards, assess the risks of those hazards, mitigate the risks, and prepare for an emergency. If you want to learn more about it, at the end of my section, I have a reference to the original description of the ramp paradigm. For handling hydrogen in a lab and for hydrogenation are shown on this table. But in particular, the flammability range of hydrogen is exceptionally broad, from 4 to 75%, and it burns with an almost invisible flame. The minimum ignition energy for hydrogen is about 1/10 of that of gasoline vapor. So it's exceedingly easy to ignite a hydrogen oxidizer mixture with static electricity. The expansion ratio is quite large. 1 milliliter of hydrogen expands to about 848 milliliters of gas at STP. Hydrogen is unique among the gases in that its Joule-Thomson coefficient is reversed. It's less than 0. That means that when hydrogen is released from high pressure to STP, it gets hot, not cold. And in fact, it gets so hot that the hydrogen at the point of release can ignite. Hydrogen presents hazards to humans in that it's an asphyxiant, but the big one is fire and detonation. In addition, hydrogen dissolves in many metals and causes metal structure changes, leading to hydrogen embrittlement and metal failure. Hydrogen, particularly in cylinders, is covered by a number of regulations and codes. Some of those are listed here. I'm not going to discuss them in this presentation, but if you have hydrogen in your facility, you really need to be cognizant of the codes and regulations and follow them as applicable. Hydrogenation has all of the hazards associated with hydrogen as part of it. Plus, as Richard indicated, typically you're working at elevated temperature and elevated pressure. These two parameters increase the risks. Hydrogenation has a real potential for creating hydrogen oxidant mixtures. The oxidant is typically air, but it can be oxygen directly. And you need to control the chemistry because of the potential for either runaway reactions or unstable intermediates. Plus, during hydrogenation, you have to deal with the catalyst, which is frequently air sensitive, which have few, if any, easy neutralization methods, and you're working in a solvent which contributes to the fire risk. The photographs on this slide illustrate two incidents which happened with hydrogen-air mixtures or hydrogen-oxygen mixtures. The incident at the University of Hawaii and the incident at the University of Missouri both resulted in explosions. The Hawaii incident involved a serious bodily injury. The Missouri incident had no injury, but did have significant property damage. With the catalyst, as shown on this slide, have a potential for a fire. This resulted in a trash can fire when the catalyst was improperly disposed of. The catalyst was pyrophoric and ignited. Using the RAMP paradigm, the A is for risk assessment. Looking at the hazards associated with handling hydrogen, the fire explosion hazard of hydrogen with air or oxygen mixtures is moderate to high. Ignition, either by thermal runaway reaction or by unstable intermediates, is also a moderate to high event. Catalyst fire while being separated or recovered is generally considered low to moderate. And the risks associated with loss of containment are considered high. The frequency of loss of containment is relatively low, but the outcome is usually quite catastrophic. Mitigation of the risks associated with hydrogenation can be really well accomplished by reduction in the quantity of hydrogen. That is, eliminating the cylinder and replacing it with a hydrogen generator. The risks that are reduced include detonation, detonation intensity, fire intensity, and fire spread. Mitigating the risks of handling the catalyst and the catalyst air reactivity can be reduced by proper handling of the catalyst using a well-established standard operating procedure. This reduces fire frequency, sparking associated with mishandling of a catalyst, and fire intensity. Mitigating the risks associated with loss of containment can be done through proper installation and inspection of fittings and piping, using well-trained personnel and high-level supervision. Reducing the quantity of hydrogen also reduces the risks associated with loss of containment by having a small reservoir, that is the hydrogen in the hydrogen generator, lower storage and operating pressure, and in particular, by reducing the pressure to the pressure generated in a generator, reduces that reverse Joule-Thomson effect fire potential. There is a rich body of literature on the safe handling of hydrogen. Here are some relevant references, particularly associated with the material that I covered. Eliminating the cylinder removes many but not all risks. Good lab practices, well-trained personnel are essential. Now, let's look at some real-life applications. I'll return it to Richard.
Thanks, Neil. So yeah, as Neil said, what we're going to do now is talk about a few user cases. And what we're going to do is we're going to start off with how we can actually apply a hydrogen generator to a pressure vessel to sort of limit the hazards of using hydrogen cylinders. Now, when we look towards designing the H-Genie, we wanted to make sure that it could be compatible with any particular system that you would actually utilize in the lab. So that's also one of the reasons why we designed it to be able to go up to almost 1500 psi. And in this particular case, what we're going to do is we're going to show it connected to a pressure vessel. So in this case, it's a power reactor. Now, what you should do before this step is to follow the sort of procedures and outlines that Neil alluded to in his presentation to make sure that everything is flushed with nitrogen, all the catalyst has been safely added before you go anywhere near adding hydrogen from the hydrogen generator. So once that's done, what you do is you make sure that it's connected and all the lines are full of hydrogen. Now, another aspect of safety which is often overlooked is actually to try and make sure that the procedures themselves are simplified, because if you overcomplicate things, that's also where accidents can kind of happen. So what we did is we tried to simplify it as much as possible like you have on a smartphone. And so what the user would do is the user would simply select batch for something like the power reactor, hit the reaction pressure, and the flow rate, which goes up to 1 liter per minute, and then press start. And then what you would do is once the reaction pressure has been reached in the line, you would actually open the line into the vessel itself and then wait for the hydrogen to fill up the pressure vessel up to the set pressure. Now, it's very important to actually look at this, and one of the sort of things we wanted to do is we wanted to give people the ability to monitor hydrogen consumption, because sometimes in a sealed pressure vessel, sometimes you don't know if your reaction stopped or it's still ongoing. So what we do is we actually have a pressure sensor at the end of the H-genie which monitors the pressure of hydrogen within the pressure vessel itself. And so if the hydrogen pressure goes down, it will monitor this and actually feed it back up into the set pressure, and then it uses the mass flow controller, which is actually inside the H-genie, to keep a count of this. So what you can do is monitor how much hydrogen is consumed during the whole of the reaction. And then during the reaction itself, what you see is you sort of get data a bit like this. It will tell you how much pressure is actually in the vessel itself. And with the reddish orange at the bottom, it will show you how much collectively the hydrogen is being consumed in the reaction. So you can actually utilize that for different kinetics studies. And what happens if it actually plateaus and you don't get any more hydrogen absorption? What will happen is that the H-genie will recognize that and will stop the reaction automatically. And then what you can do at the end of the reaction, you can actually export all this data into a CSV file, so you can actually put that into one of your lab notebooks. Okay, so that's a very simple way of actually how you would perform a reaction with a pressure vessel. What I'm going to do now is hand off to Gellert Schiebosch, and he's going to sort of detail some of the more complicated and specific chemistry that he's been looking at regarding performing hydrogenation and making novel molecules.
Thank you, Richard. It's Gellert Schiebosch talking. I am an associate principal scientist at Cominex. And today I will talk about Cominex's approach towards hydrogenations for technology-enabled library synthesis. Cominex is a drug discovery service provider with more than 25 years experience in working with top pharma companies from the US, Europe, and Japan. We also have some customers from the biotech and agrochemical industries. Our key expertise lies in library synthesis, such as the synthesis of screening compound libraries, fragment libraries, or target-oriented libraries. In more recent years, we initiated research in DNA-encoded library synthesis. Apart from library synthesis, we also do work based on fixed fee or FTE-based custom chemistry, and we perform batch-to-flow process reengineering as well. During our adventures, we tend to use a unique combination of technologies and know-how. We were amongst the first adopters of flow chemistry, and we built up quite a big experience in high-performance hydrogenations. Hydrogenations are amongst the most frequently performed reactions, and today I will only focus on a special aspect related to hydrogenations. It has been recognized in the last 15 to 20 years that too many aromatic rings can lead to higher attrition rate in drug development. This recognition generated significant interest in molecules with lower aromacity. One way to access compounds with high FSP3 content or high 3D character is to use a flat heteroaromatic structure, perform a reduction sequence using hydrogenation, and by this you can increase the 3D character of your compound. As you can see on the top right of this slide, the log P, log D, and solubility of the compound can be tuned using this technology. Our chemists at Cominex performed a large number of test reactions in order to build up a know-how. Using this know-how, Nowadays, we are able to tune the reactivity, chemoselectivity, stereoselectivity, and the residual selectivity of hydrogenation reactions with a good chance to succeed. On this slide, you can see a brief overview on the technology which we use during our hydrogenation reactions. We apply traditional batch pressure vessels for hydrogenations, and we also perform reactions using modern flow chemistry instruments such as the HQ Pro, which is a standalone benchtop hydrogenation reactor. Since Thales Nanoenergy developed the H-Genie, we started to replace the cylinders in our lab. We use the H-Genie in combination with pressure vessels and with flow reactor technology, such as the Phoenix flow reactor as well. And to be honest, we occasionally just use the Genie to fill balloons for low pressure, small scale applications. On the bottom of this slide, you can see a brief selection of the typical conditions in which we operate. In terms of catalysts, the most frequently used is palladium on charcoal in our labs, but we quite often use rhodium on charcoal or ruthenium on charcoal and Raney nickel as well. The pressure range in which we operate is between 1 and 100 bar, and we rarely go above 150 degrees Celsius in terms of temperature. On the next two slides, you can see a couple of examples on how to tune the selectivity of a certain reaction or problem. So in this instance, one can end up with either product A or product B, depending on the conditions to choose. For example, we produced product B with good selectivity using platinum dioxide as a catalyst under batch conditions. On the other hand, product A was produced with 100% conversion under flow conditions using palladium on charcoal as the catalyst of choice. Performing reactions stereoselectively can be of high importance. For example, we had an FD project in which we needed to produce dye-substituted piperidines. For these, we used dye-substituted pyridines and starting materials. As you can see on this slide, by choosing the right catalyst, we were able to tune the selectivity to either to the trans or the cis product in most of the cases. On the following two slides, you can see a collection of some interesting structures or scaffolds which we have prepared during using hydrogenation technology as the key enabling step. I don't have time to go into details regarding these structures, but if you are interested in these compounds, please visit the slides later on. So using Cominax's hydrogenation synthesis platform, we can prepare novel fragments, building blocks, or screening libraries with high FSP3 character. And although this is interesting scientifically, it is quite useful for business. Cominax created a consortium called the Technology-Enabled Compound Library Consortium, consisting of 3 industrial pharma companies and a non-profit partner. For these 4 partners, we altogether prepared 40,000 individual novel compounds in a 3-year time period using hydrogenations as the key enabling technology. And with this, I will thank you for your attention, and I will hand over the words to René.
Okay, thank you very much, Gilad. Let's continue with the last case study for today. In this part, I would like to present a scalable continuous flow hydrogenation using catalytic static mixers. So to give you a little bit of background information first, in one of our current projects, we are developing a model-based control strategy for a multi-step API synthesis. And in close collaboration between academic and industrial partners, we are building process models from reaction data. These process models are then used as basis for our control software, which is able to manipulate various process parameters of a continuous flow reactor setup. And the resulting response of these reactions can be captured by process analytical technology and is then further fed back into the control software. For more information on this project, I would like to refer to our homepage at the bottom of this slide. One of the key steps of this multi-step synthesis is a hydrogenation reaction, which is carried out in this lab-scale reactor, which features a total of 8 rectangular channels. Due to the flat geometry, as you can see in the picture on the right, the channels reach heat transfer coefficients of up to the range of 10 kilowatts per square meter Kelvin. And if you want to scale up this reactor, the channels are bundled in parallel while their cross-section hardly changes. And to further enhance the mass transfer, they are filled with static mixing elements. Our goal for this project was to replace the initial mixing elements by catalytically active ones. At this point, we started to collaborate with the team around Christian Hornung from CSIRO in Australia. In recent years, they gathered a lot of expertise in manufacturing so-called catalytic static mixers, which are also referred to as CSMs. They developed different mixing structures with large geometric surface areas by additive manufacturing techniques, and they also immobilized different catalytically active transition metals on them. Most of these CSMs have been obtained either by electroplating or by cold spray techniques, but also by slurry coating, as you will see in this presentation. So the workflow begins with constructing the CAD models according to the geometric demands of the reaction channel. And we have two main objectives, which are either on one hand promote multi-phase mixing and also maximizing the coatable surface area of the mixers. In the next step, the mixers were printed from 316 stainless steel by selective laser melting and then coated by the catalyst, and in this case an aqueous palladium alumina slurry was applied, and then the mixers were heated and dried in a vacuum oven. And finally, they're characterized via scanning electron microscopy using different modes. So on the bottom left, you can see the CM images and the EDX image corresponding to a typical stainless steel composition. And on the right side, you can see the mixer after the coating process, which shows a homogeneous layer of palladium on alumina support. Next, the mixers are shipped from Australia to our labs in Austria, where they are inserted into our hydrogenation setup, which consists of an HPLC pump with an integrated pressure sensor for the liquid feed, the HGenie hydrogen generated with an integrated mass flow controller, and both feeds are mixed directly before the flow reactor. The flow reactor itself is equipped with both catalytic static mixers and also the standard mixers to enhance gas-liquid mixing. And the temperature of the flow reactor is regulated by an external thermostat. The pressure is regulated by an adjustable back pressure regulator. And at the output of the setup, we use a gas-liquid separator to remove excess hydrogen. And to evaluate the performance of this setup, we chose a model reaction, namely the hydrogenation from nitronaphthalene to naphthylamine. At the beginning of a reaction parameter screen, we selected a suitable solvent based on solubility tests of substrate and product. We considered Chem 21 recommendations, and we conducted some preliminary hydrogenation test runs. Based on these criteria, we reduced our choice to ethyl acetate and ethanol. And when we started to monitor the conversion to the desired product over time, we typically observe an initial drop in conversion based on the fact that the reactor is purged with solvent and hydrogen under the reaction conditions, which actually maximizes the amount of hydrogen absorbed by the catalyst. However, after about 2 hours of operation, we observed that reactions carried out in ethanol reach a stable plateau compared to other solvent combinations. We assume this is based on the protic character of ethanol, which helps to wash out the formed amine from the porous alumina layer. And as expected for these kinds of hydrogenation reactions, both elevated pressure and temperature are beneficial for a fast conversion. In this case, we are typically only limited by the hardware specifications of the setup. Next, we turn our attention to the influence of different gas and liquid flow rates. So therefore, we started to test 4 different liquid flow rates, which are depicted as QL in this graph, versus 4 different gas flow rates depicted as QG. And what we found was that there is a clear correlation between the liquid flow rate and the conversion. However, changing the gas flow rate between 25 and 100 milliliters per minute did not seem to have any substantial influence on the conversion. So at this point, we assumed that this is based on the low flow rates, which are used for this reactor, that they give some sort of annular flow regime where the gas can pass in between the liquid, and therefore the gas flow rate does not affect the overall residence time. So to prove this, we conducted some residence time distribution experiments, and to cut a long story short, we observed that the mean residence time only changes by a small factor compared to the change in gas flow rate. So note that all these experiments so far were only conducted with 1 CSM, which filled half of a 30 centimeter channel. When we started to increase the amount of mixers to 4, we also wanted to increase the flow rates by the same factor to achieve similar residence times around the catalytically active zone of the reactor. And the result was quite impressive, as we observed conversions above 96% for all tested flow rate combinations. So for example, if you have a look at the purple data point for 8 milliliters per minute liquid flow rate and 200 milliliters per minute gas flow rate, you actually have a conversion of 97% to the desired amine using the 4 CSMs, whereas previously, when you look at the data point at 2 milliliters per minute liquid flow rate and 50 milliliters per minute gas flow rate, which is exactly 1/4 of these flow rates, you only end up with 70% conversion. Using this setup, featuring 4 CSMs, we wanted to demonstrate the potential of this process for the synthesis of active pharmaceutical ingredients. Therefore, we investigated the hydrogenation of chloronitroaniline to chlorophenyldiamine, a key intermediate for tizanidine, which is used as a muscle relaxant. We operated the process at a concentration of 0.1 mole per liter, 4 milliliters per minute liquid flow rate, and 100 milliliters per minute gas flow rate. Under these conditions, we typically observe excellent conversion to the desired product and only minor formation of the dehalogenated phenylenediamine. To isolate the product, we conducted an 8-hour run where we started with an equilibration phase where the system was purged with only ethanol and hydrogen at 100 milliliters per minute for 1 hour. After 1 hour, we switched to a substrate solution and collected the product for 8 hours in a row. And you can see the corresponding hydrogen flow rate plotted in turquoise on the left y-axis, and the output pressure plotted in purple on the right y-axis. The workup was actually very simple due to the heterogeneous catalyst, so we only had to remove the solvent under reduced pressure, and we could isolate the product of this hydrogenation reaction in 96% yield. Ultimately, I briefly want to discuss the stability of the CSMs. So first of all, we've been using the same CSM for all initial studies, which took place during 2 months. And during that time, we never observed any distinct decrease in activity. And also during that period, the weight of the mixer stayed essentially the same. So we compared the weight before the first insertion into the setup, after all the optimizations were done, and the weight stayed essentially the same. And in addition, we also conducted ICP-MS measurements for selected conditions, which are either ethanol solvent purge or hydrogenation reactions. And from the table below, you can see that there was essentially no leaching of either the palladium alumina catalyst or of the stainless steel scaffold taking place. So to wrap things up, the static mixers were specially designed and tailored for the scalable microbial lab reactor. They were coated with a palladium catalyst on a porous alumina support, and we found stable reaction conditions for our model substrate. The reaction is very much mixing dependent, which is based on the different gas and liquid flow rates. And using the optimal conditions, we were able to isolate an API intermediate for titaniidine, and the mixers are very stable and essentially no leaching of the catalyst takes place. At this point, I would like to use the opportunity to thank a few people, especially Professor Oliver Kappe for taking me into his group, Christian Hornung and his team at CSIRO in Australia for their excellent collaboration, as well as our funding agencies. With that, I would like to thank you very much for your kind attention and leave you with an overview of our partners within the CC Flow Consortium. And now we are ready for questions.
Thank you so much for this presentation. And now we will open it up to some questions. The first question is, Renee, what is the scale you would like to go up to in flow, and what type of reactions would you like to try next?
Thank you very much. It's a good question. So with the setup you've seen here, we've only been using 4 catalytic static mixers so far. However, the reactor is able to hold up to 16 CSMs. So actually you could increase all the flow rates by a 4-fold. And as we have seen, we have still quantitative conversion. We're actually optimistic that we could even go higher with the flow rate once 16 mixers are inserted. And about the reactions, we just want to look into other substrates and other hydrogenation reactions. Maybe different nitro groups or different nitriles, but we will see about that.
Okay, thank you. This question is for Neil. Based on your experience, what mistake has caused the most accidents with hydrogen?
Well, thank you. There really are 2 general areas. One is loss of containment, primarily leaks coming from the tubings, the fittings that are either improperly installed or improperly maintained. And the other that's generally more substantial is bodily injury, strains and bruises and bangs and things from wrestling with the cylinders. Even using a proper hand truck, moving a cylinder can be challenging, particularly for a person of relatively small stature. So maintaining the equipment and proper handling are the big preventative actions. Thank you.
Thank you. This next question is for Gallet. Were all the compounds in the libraries you created novel?
Thank you. Yes, they were all novel. We had a number of design criteria which we have to comply with, and novelty was one of the key criteria. Thank you.
Okay. You mentioned the solubility of hydrogen being rather low. We use balloons in my lab currently, and I was wondering what I could expect if we were to start using pressure vessels instead. Can you go over what I can expect to see if I start using higher pressure?
Yeah, so this is Richard Jones. I think I can answer that one. So yes, so when you start using reactions with balloons, you're limited to typically reactions regarding room temperature and 1 bar. So you're quite limited in terms of the functional groups which you can actually convert. So if you were to utilize pressures, you're able to utilize higher temperatures. This will both increase the rate of reaction, and it will also open the chemistry up to some of the more difficult type reactions. Maybe it's hindered double bonds or potentially heterocycle reductions or maybe nitrile reductions as well.
Thank you. Another question is, how is the H-genie able to determine when a reaction has run to completion?
Yeah, that's a pretty good question, actually. So what it does is it actually monitors, it has a pressure sensor, and it monitors the pressure of hydrogen within the pressure vessel. And so once the pressure starts to decrease, that means that the hydrogen is being consumed in the reaction. So what it does is it uses the pressure sensor in combination with a mass flow controller, which basically counts how much hydrogen is being put into the reactor. And once it shows that the pressure stays constant and no more hydrogen is being fed into the machine over an extended period of time, that means that it shows that your reaction is finished.
Okay, another one is, have you tried other catalyst supports apart from charcoal?
Hi, it's Gallet speaking. I guess this is for me. So we have tried other supports as well, like alumina, that is one of the classical ones. And sometimes we use polymer supported catalysts as well. Thank you.
Okay, thank you. Here's another one. Have you used the H-genie with other isotopes like deuterium and tritium?
I'll take that question. So yes, you can actually, we've utilized it with deuterium gas. So that can be done pretty easily, actually. So you generate, so the same as in terms of hydrogen gas purity, you can generate gas purity up to 99.99%. So with deuterated water, you can generate deuterium gas up to 99.99%. We haven't tried tritium because it's highly radioactive and extremely dangerous. So we just stick to deuterium, which is pretty inert.
Okay, and this is the last question that we have. Can a small-scale hydrogen production be set up on a small-scale ammonia plant, such as on a farm?
That's an interesting question. We have had questions like this before, actually, sort of offline, and the answer, I guess, is yes. So all you need is you can run sort of a typical electrolyzer technology like the H-genie off a standard electrical supply, and all you need is deionized water to do it. So yes, you can run this sort of system at home, I guess, but I'm not sure I recommend it at this stage. But we've also had people interested in being able to utilize solar energy generated in the summer store hydrogen to use for fuel cells in the winter. So that's another application which is also being used as well.
Okay, thank you, and that's all the time we have. Thank you again to Richard Jones, Dr. Neil Langerman, Dr. Gallet Schipos, and Renee LaBelle for your fascinating presentation. And thank you all the participants for being a great audience. Be sure to check CNEN and CNEN Online for information on the next edition of CNEN webinars. Thank you On24 for technology and production services, and thank you to Heidolf North America for the sponsorship that made this interactive webcast possible. For CNEN webinars, I'm Melissa O'Mara. Goodbye.